We are beginning with the part C of unit 1. We have finished part A, part B, and now we are beginning part C. The topics under part C includes substituents, effects of substituents on reactivity, and orientation of mono-substituted benzene towards electrophilic substitution reaction. This means we have to study about substituents and the effect of substituents on two things. One is reactivity and the other is orientation. So let us see what we are talking about. So in the first part, you have already studied that benzene derivatives are the ones on which some groups are present. And now this derivative is called the benzene derivative, isn't it? We have discussed it. Hydroxy on the benzene is called phenol. Methyl on benzene is called toluene. So such are the substituents that we have. And many kind of substituents we have already studied. In the part B, we have covered electrophilic substitution reaction. It means we have covered how a hydrogen of the benzene is replaced by an incoming electrophile. So the product that has just formed is called mono-substituted benzene. Now the interesting thing of part C is that when this mono-substituted benzene is going to undergo one more round of electrophilic substitution reaction, then what is the effect of this already present substituent on the rate of the reaction that it will undergo and the position of the incoming electrophile? Rate means whether the reaction will become more easy, the reaction will speed up, the things will become easy. Is it the effect of the already present electrophile on the second round of electrophilic addition? And the second thing is orientation. That means the incoming electrophile, whether it is going to add on the next position to the already present electrophile. This is called the ortho position. Or whether it is going to add to the next position of the electrophile, that is called the meta position, or the next to the next position, which is called the para position. So this is the effect of already present electrophile, or you can also call it substituent, on the incoming electrophile. Okay, so these two effects we have to study. This is what is written on the text over here. Now let us start discussing the effect of substituent on one part, that is reactivity. So with reactivity we mean whether the reaction, the second reaction, is going to get easier. Will the reaction rate increase? Or the reaction rate will decrease and the reaction will get tougher? This will depend upon the already present substituent. So whether reaction rate can be improved, this group would be called activating group. Otherwise the reaction rate will decrease, then the group would be called deactivating group. Now one important thing for you to understand is there is a relationship between orientation and the reactivity. All the groups which direct the incoming electrophile on the ortho and the para position are activating groups. It means those groups which are going to direct the incoming electrophile on ortho and para positions are always going to increase the rate of the reaction. That is why such groups are called activating groups. On the other hand, the meta directing groups, the groups which will always direct the substituent on the meta position, are always going to deactivate the benzene ring, and it means decrease the rate of the reaction. So that is why these will be called deactivating groups. So there is a relationship between orientation and reactivity. Ortho and para directing always increase the reactivity, meta directing always decrease the reactivity. It goes hand in hand, the relationship between things. It's just like having a face. Like Narendra Modi is the face of Bharatiya Janata Party. So Modi is Bharatiya Janata Party and Bharatiya Janata Party is Modi. Similarly, this is the effect of influence. Similarly, the ortho and para directing groups are always activating. It's a fixed relationship. The meta directing groups are always deactivating. It's a fixed relationship. Okay, how it is done? The orthopara directing groups, they increase the electron density on the benzene, so they makes the benzene more nucleophilic. As we have already studied, the benzene act as a nucleophile and the reagent act as an electrophile. So that is how the two things are reacting with each other. So anything which makes benzene more nucleophilic is always going to increase the rate of the reaction, because that will favor the reaction. So ortho and para directing groups always gives the electron density to benzene. So that is how the benzene ring gets activated, and it always increases the rate of the reaction. On the other hand, meta-directing groups always withdraw electrons from the benzene, so thereby they decrease the electron density. That means they deactivates the benzene ring for further electrophilic reaction. So these groups are called deactivating groups. One example that you can very well understand this concept is, suppose we want to do nitration of benzene and its derivatives. Nitration means NO2 group has to be introduced. So you have 5 players. Suppose you want to do nitration on each of them. And now you can compare which of the molecule is having ease with undergoing nitration. So suppose you do nitration with benzene and you say the rate of the reaction, let's say its value is 1. Now you compare the rate of the reaction of toluene, how easily it is undergoing nitration. The rate comes out to be, it is going 25 times faster than benzene. So nitration has become easier. What was the reason? The reason was this CS3 group. Even this small group over benzene can make toluene undergo nitration 25 times faster. Isn't it amazing? This is because that CS3 group is increasing the electron density of benzene by giving some of its electron density to benzene. So that is how the reaction rate of nitration is faster with toluene. And the reaction rate even increases up to 1000 times faster in case of phenol. So such small group, hydroxy group, donates so much amount of electron density to benzene that it increases the rate 1000 times faster. So isn't it activation? This is the rate that we are talking about, the effect of substituent on reactivity. On the other hand, there are groups which can decrease the reaction rate, such as chlorobenzene. It can decrease the rate 3000 times less. Nitro group, it can decrease the rate 10 million times. 10 million times slower nitrobenzene would undergo another round of nitration. Nitro group has decreased the electron density. It is pulling away electron density from benzene. That is why benzene is less nucleophilic and it is not ready to go another round of nitration. Reaction rate had decreased 10 million times. So I hope you have understood the effect on reactivity by the substituent. We will discuss the ground basis of such effects. These such effects are having the basis in terms of physics and the electronic parameters. So we will discuss about these bases in the next session.